So what I want to do is, my background, I'm an AI nerd by training. I went to school at MIT back when it didn't work, and studied under people like Marvin Minsky. And I'm going to share a story with you that's a serious WTF moment for me. This is where the title came from. I studied AI at MIT and then at University of Washington. I graduated. I couldn't find any work. And my mom's like, what'd you just do? You spent all this money and borrowed this money to go to school, and I ended up getting a job doing web things. And I was largely retired, and a friend of mine who was at the MIT lab with me was at Google Research. And he sent me a posting on Facebook. And that posting is what I'm about to show you. You've seen it somewhere in here. And his whole posting was WTF. And my mom was looking over my shoulder, and she goes, oh, that's fine, honey. What does that stand for? And I said, wow, that's fantastic. So I'm going to show you that story. And this is the journey of Google's journey into AI. You're now seeing it here. There's a lot of hype going on. I'm going to poke through it into a fundamental concept that's from 1952. And this concept, which we demonstrated in 2013, but in 1952, the idea was, if you're going to build a computer like Alan Turing did, remember that machine, the Enigma Machine, to solve the Enigma Machine? And you can see this thing not too far from here in England. And if you look at it, it's turning these like tin cans trying to figure out the parameters to solve the Enigma. A different team said back in 1950, I know what he's doing. Those cans he's turning, those are weights on neurons. Now, the whole camp knew we're going to do von Neumann architectures and we're going to follow the ALU, which we have traditional computing, where ideas were sets. And sets became first-order logic, became programming languages. That was the entire spectrum. The small team said, no, no, no. We should be able to represent concepts like activations of neurons in your head. If that's true, we should be able to have things like a king and a man, subtract the same amount, and out comes queen and woman. You should be able to take London, subtract England, and add France, and the computer should tell you, well, Paris. And this idea was, they built a machine called a perceptron in 1958, and it sort of worked. It was the first machine vision system of its kind, and only recognized Courier 10-point font. 11-point couldn't recognize it. Bold, couldn't see it. So Marvin Minsky wrote a book called Perceptrons in 1968, largely discredited the whole area. Well, a lot of things have happened since that time. The idea of concepts, they realized that in order for us to conduct in nature, our eyes and nature have evolved over millions of years, and they have these regular patterns. And it turns out you can take these concepts, and we found this is actually very useful, and you can group them in regular patterns that from civil engineering is called a tensor. But think of it this way, if you used a spreadsheet before, right? A cell of a spreadsheet is a 0D tensor. A column is a 1D tensor, right? A sheet is a 2D tensor, right? A full sheet, not a sheet with like, where everyone's like not completely the same length, but if they're all the same length, it's a tensor. And you can stack them deep like an image, RGB, and that's also a tensor. So it turns out, if you take concepts and you map them as tensors, the idea is you can actually go from a tensor input, which is our activation from hearing, from voice, when you're speaking out, to feeling, to tensing, to reading. Take it as a tensor, and the output tensor is just another tensor like this. So for example, an input could be a picture, an output could be a long vector, and you check a box saying, is it a cat or a dog? So you have tensor in, tensor out. And what the brain's doing is it's figuring out a function to go from tensor in to tensor out using piecewise statistical approximation to the real value, which is no different than Isaac Newton or the physicists who are trying to do closed form solutions to observing the environment. Except the computer is mechanistic, and it's using statistics and probability mass to figure out that function that basically is going and reasoning in like 500,000 D. Think of that. 500,000 D, when like you and I live in a 3D world, this is 500,000 D. So what this began with is, that first thing from 1958, you've probably seen this diagram before, became deep learning, where the idea is you have a tensor coming as an image. The tensor in the output at the very top is literally just a simple column that says cat, dog, or the 1,000 things you're identifying. And then you have each layer, which is basically artificial neurons connected one to the next. And the way these things work is essentially you fill up a tensor with numbers. You either add or multiply to each different cell to the first layer. That goes to the second layer and so forth. And the learning is figuring out how much to add, how much to multiply to each little cell as you go up and down. And that essentially is deep learning. And so this technique in 2012, we first looked at it and we won a few contests. And this is the WTF moment, which you've probably seen a few times here today. This actually came from DeepMind. And the idea was, could we play a video game where concepts are vectors? So what they did is they encoded the actual game 84 by 84 pixels, and it's just numbers. It's just pixels in. And the output was a column in Excel that told you up, down, left, right, diagonal, and fire. So pixel in, pixel out, and they used a technique called reinforcement learning to actually adjust the weights so it figured out the game function. And when you first start it, it's sort of randomly trying to figure out what to do because it doesn't know what action to take, and every now and then it gets a point, and it gets just pure dumb luck. After just 120 minutes, this game was demonstrated in 2013 to be flawless, even hitting things that are almost impossible for humans to hit. And the thing we've talked about, you've seen in the opening keynotes, is this game actually figured out a strategy where if you dig a tunnel purely on tensor to tensor, it figured out to dig a tunnel, you get the biggest high ever, the biggest highest reward. So we saw this in 2014 and 2013, and some engineers said, let's do this, let's have some fun with this. Let's take that network here on the left, called an encoder. So here's the input image from the video game, and the output is like the joystick. Let's do what our parents do, let's play it backwards. Let's play it backwards. So this thing in the middle, they call that a concept, a precept, an embedding. They said, this represents the concept of the game. What if we play the thing backwards, and we now have a computer to tell us what every pixel is in an image? And they tried this. So they take an image, and you're trying to do here on the right, so imagine that instead of pixel movements, they picked 18 things: sky, building, pole, road marketing, so forth. And they painstakingly labeled it, and the idea is you take a video, you capture it frame by frame, and you first encode it, then you decode it, getting hints from the first picture. And sure enough, with a supercomputer running overnight, you can take a video, slice it up, and you start to get something that looks like you've had too much to drink. But you can start to see, like, the purple's the road, and it's not quite perfect. This is 2015. So now you're not just saying what the joystick is, you're having 18 things in this scene. The Chinese saw this and said, bet we can outdo that. This is at 30 frames per second, running on a desktop computer, right? Essentially almost pixel perfect, nailing it. And that is only 2 years later. So it's gone from toys to actually doing this. And some people on Android saw this and said, well, that's cool, but what else could we do with this? Well, let's make it even more efficient. Let's run it, and let's run it basically on a mobile phone. So here you have an image. It's able to figure out the backdrop, and as a result, be able to do things like you're on vacation, and you can put your office behind you and say, yeah, honey, I'm working hard, right? So when we saw this at Google, Jeff Dean, our chief engineer, said, what about doing something useful with this? How about, I like Fei Li, who's our chief scientist. I want her to speak Chinese. I want to hear Texas drawl. I want to speak Texas drawl. She should hear native Chinese. That's 6 networks. Chinese, Chinese text to English text to voice, native, and then play backwards. He said, if you do that, it's billions of operations per second on a phone, times a billion users, we're going to smoke all of Google. So he told the board this, and they said, well, the first thing I want to do is I want to have the world solve this problem, if this is true, if concepts are vectors. So I'm going to take my tensors flowing through my network, the internal name of that code was called Google Brain. They renamed it TensorFlow, and released it. And then he said, we have to rethink the chip. So he built this chip that actually just does the operations of a neural network, called a tensor processing unit, first to serve it and then to reason it. And the recent one, we now have these bricks that are half as powerful as the most powerful supercomputer in the world. And we release these bricks one after another. I can't tell you how frequently, but rather frequently. And this is what we have set up that's on fiber, that's custom fiber that we actually drag across the oceans with our own Google Navy. And then what we did is he said, how are you going to run this on this infrastructure? How do you program this thing? Well, we tried virtual machines, which you've seen before in cloud. And bare metal server, they went to virtual machines, and that wasn't performant enough because it takes a few minutes to cycle one up. Then we went to containers, which have application code and dependencies. And now we're moving to service, which is basically container free. You're now thinking about services. And we found for machine learning is that when we're serving something at the very top, essentially is the actual image you're doing on top of Jupyter notebooks, that sits on things like TensorFlow, Python, CUDA, and NVIDIA if you're doing that. And the point is, AI is changing so fast. What you want to do is focus on the top and swap these things out. That's what containers give you. It's a layered file system, so as you swap it in, we very quickly can do this. And then we wrote a system that goes from a onesie all the way to billions of these things operating across that infrastructure. So as a programmer, you live in this environment, but you're running inside something on the right. With that, we decided to go after some real problems. And one was email. Could we actually use an AI to do email? And here the idea was you encode an email as a tensor. The output tensor are the first 10 words you type in response to that. We trained this on Gmail, released it in Inbox, and you see it as 3 suggestions on the bottom here. It's purely deep learning, the same thing that played the video game, same math, now figures it out, and within 90 days, 1 out of every 8 emails is being responded to by the bot. The next thing we did is we took the research and we lit it up, and now we replaced years and years of stitching together voice by voice samples, and it's called WaveNet. We now produce from a raw waveform, the same way I showed you where you have the encoder, the decoder, we now actually generate human-like speech that you saw at I.O., if you may have seen that, where it's indistinguishable from human voice. You can actually put Texas drawl or local Chinese dialects on the voice. And we released that, and now you can actually do conversational demos you might see at the Google Cloud booth, where you can speak in 7 languages and have it translate in real time. The next thing we did, when we showed us the business, they said, well, that's not really business, because business is about gut feel. So I think this basically pissed off the engineers, and so they went after a game that's all gut feel called Go. The game's so complex, it's one of the 4 things Confucius said you should master as a human being. And if you ask the top player in the world, hey, who's winning, like Lee Sedol, he'll say, white. And you'll say, well, why white? Is it a classic opening you're seeing that? And he goes, no, it feels right. And you ask him, well, where would you move? He'll look at it for a minute and goes, well, clearly here. And you say, well, why? Is this a classic move? Is it a block? Are you trying to, he goes, no, it just feels right. So we took 20 million games from South Korea, and we trained an AI that I was able to figure out the feeling function from input tensor of game board, who's winning or losing, not cat or dog, winning or losing, tensor function. The tensor function from, here's a game board, 172, not classifying it, where do you put your stone? 2 functions, that's all it was. But where we're finding money and we're finding business value is now using this, the same technique that we use to identify cats and dogs, we're using it to identify you and me. The idea is that you can actually stack your behavior of how you browse or how your people come to your websites and your mobile, and stack that into a tensor like an image, and the output tensor is, what do you think she's going to do next? And as a result, you can actually have personalized models of behavior, and you can do it across all different devices, so you can get actually instantaneous responses that people want, because it's all math. And we do this all the time, all day long, and we just replaced this starting in 2014. So we have these 7 different properties, each with over 1 billion different users, all running on that one platform inside those containers I talked about. And what's actually happening is you can actually create this for yourself. As I'm talking, and some of you are probably on your phones, you're searching, you're actually creating digital exhaust that's being ingested around the globe. It's petabytes on every so few many minutes. We then actually explore that in something called BigQuery. We then prepare that, so you're taking the raw data as it comes through, you're turning it into tensors. In the tensors, you have thousands of different variations of tensors that are figuring out a model to say, what's the next YouTube video? What's the next response? What's the next Google Play? That then goes into your home, for example, and that creates more exhaust, and it repeats. This is happening in real time, and what we're doing is bringing all these techniques that we've honed over the last 3 years out to market. And so what you can do, if you wanted to try some of this yourself, we have a business we've called Google Cloud that's trying to take this $30 billion investment we've done for ourselves and figure out that we think other people might find this useful, to do computing where you're doing computing with tensors, and that's what Google Cloud is. And you can actually use our models, or you can go create your own. So in other words, we've got ways to go from tensor to tensor for images and ways we reason and read text and whatnot, but you can also do it for business. Or the idea is you can actually train your own using your own containers. And so if you want to figure out how to get started, we have these models you can use as very simple RESTful APIs that we're trying to do the basic modalities of human condition. So that you can now, for the first time, look at your processes and have computers that can literally see, they can read, they can speak, and they can actually start to reason. So think of all your processes where you have humans doing this and in boring jobs, you can start to use this to start to make those jobs less boring and more exciting. The next thing is you want to create your own models. When we were talking to the board about this, they said, well, what's the next big challenge? And Eric Schmidt said, I know one. Make an AI that does your job. Your job. And so we tried this, and the idea was if you have a tensor going to a tensor, it's flowing through a graph like I showed you before. So the research said, let's go create an AI that sits on top and systematically goes through graphs that figures out the best performance, like an AI creating an AI. And we did that, and what this graph shows is the graph size versus performance. Yellow is 20 years of human research. Blue is 20,000 iterations on 500 TPUs running over 8 weeks. And as a result, we're finding that it creates smaller models more performant than the best models in the world coming out of China. So that's called AutoML. And the next thing is, if you want to play with this, there's a technique that our Google research team has released. It's from the Python notebooks, or you've seen Jupyter notebooks. It's called Collaboratory. And this is sort of a research project that allows you to actually sit on top of that massive infrastructure and play. So this is part of our contribution to Google and TensorFlow. It's called Collaboratory. Let's sort of get started with this. And the commercial version of this is called KubeFlow. And what also we'd like you to do is to think about joining in the fun. The largest community, think of like GitHub, and you saw recent activity around GitHub, largest community of open source developers. The largest community of people who know how to do this, tensor to tensor and do that sort of reasoning, they're congregating in this community called Kaggle. And what they're doing is they do this to sort of hone their own skills, but some of the best data sets in the world are now being accumulated here, and it's probably the best repository of sample data and sample experts. And it's highly collaborative, and Kaggle is a combination of GitHub plus storage on Google Cloud and Amazon, and actual contest, you can actually see the work. And so if you're looking for something, chances are you can start here, find someone to collaborate, and take the next step. So that's the end of my quick 20-minute intro, and I hope maybe you see it now, but the idea is that we're now starting to see at Google that the core of our business is now being run and driven by the idea that we're actually reasoning in a space where concepts are continuous vectors. And we think we're just getting started with where we can actually take that. And if it seems like a radical thought, it was when I first saw it. This was a serious WTF moment. But that's something very real that we feel is going to be as common as a database in only a few years' time. So thank you very much for your time.